I can just share when you tell me to, I guess.
Yeah, I will tell you.
Yeah.
I can see the screen is gone up now.
I can just share.
Okay, ladies and gentlemen, we will start this session. And the first speaker here is Knut Emil Ringstad. He is working as PhD at NTNU in Trondheim in Norway. And he's working with modeling and components in refrigeration systems using natural working fluids. Knut, the floor is yours.
Thank you. Let's see. Can you see my screen?
Yep.
Perfect. Good afternoon, everyone. My name is, previously mentioned, is Knut Emil Ringstad. I'm a PhD student at the NTNU in Norway under Armin Hafner, and I work in a research project called HIF. And I will today present to you some of the work we did last year in a work called Comparative Study of R744 Ejector CFD Models. Let's see if I can, there we go. The content for today is I will start with a more general introduction on CO2 ejectors, their application and why we want to explore CFD models for these types of components. I will then move over to a overview of the available models that we're investigating in this work before I display the test case we're using and quickly go over some of the results and the discussions before concluding and looking forward. For more details, of course, see the article. So just to introduce the topic, in the last years there has been, as many of you of course know, a large growing interest for CO2 ejectors. And this is because of their massive potential for COP improvements, especially at high ambient temperatures. And while they can do this at a very low cost due to their simplistic design and very low cost due to no moving parts, which means low cost as well. However, their performance is very sensitive to their design. Any small change in the ejector geometry can make massive differences in ejector performance. And this is why so much emphasis has been put on CO2 two-phase ejectors and understanding and modeling their very complex flow features. Some of the features that we have to consider are supersonic flow, multi-phase flow with phase change, and a complicated phase change type that's called flashing, and also quite advanced thermodynamics in the sense of non-equilibrium and supercritical states. So there's been a lot more focus on advanced CFD or thermodynamic models for CO2 ejectors, and also on how we can use those models in design algorithms. So as you may be aware, there are many CFD models available for multi-phase flows, and many of these have been used for CO2 ejectors. Some of the most prominent ones we find in literature are the homogeneous equilibrium model, homogeneous relaxation model, HRM, different types of mixture models, and we recently presented a two-fluid model to try to get a good modeling of the CO2 ejector. These different models have varying accuracy and also varying computational costs. While all can give you pretty decent results, they can vary in computation time from 1 hour to months. To make this even more complicated, the accuracy also depends on the operating conditions under which you simulate your ejector. So for example, for high pressure conditions, equilibrium models are typically better than other types of models. So I will, in our work, we compared some of these most prominent models for a specific test case. And I will now quickly go through what the different models are and the difference between them. The first model is the HEM, or the homogeneous equilibrium model. It's a quite simple model because it assumes full equilibrium of both liquid and gas phase. This means that they are assumed to have the same pressure and temperature and also velocity. And these are typically quite accurate for supercritical motive conditions. While when we move down to the relaxation models, here instead of assuming that the phase fraction is at equilibrium at all times, we have to model the phase change as a relaxation process towards that equilibrium. That relaxation process is governed by a relaxation timescale, which has been extensively studied in the previous works. And we use one of the more complicated models in this comparative work. The third model is called a mixture model. Here we use one of the more advanced mixture models available. It's a mixture model essentially is where you, instead of modeling the phase change process as a relaxation toward equilibrium, you use a specific submodel for modeling this phase change. This model is based on something called a UDRGM, which is a specific and very complicated to use thermodynamic library in ANSYS Fluent. And this has caused it to typically have very slow convergence time, but still, when you actually get convergence, you will typically have very high accuracy. And the last model we compared is the two-fluid model. This we presented last year, and instead of modeling the flow as a meaned flow of the liquid and gas phase, you actually solve a separate set of equations for each phase. And then you couple those equations together using different, typically more complicated relations for friction, mass transfer, and heat transfer. And in this work, we used a similar thermodynamic library to the UDRGM, but we simplified it, for example, by removing some gradients to improve upon convergence time. The test case we're looking at is an experimental test case from a previous work by Palach et al. In 2017. We choose 4 operating conditions from their experimental campaign that cover a range of operating conditions that the ejector will show the difference in accuracy for different operating conditions. The numerical solver is, of course, of interest. Here we use the CFD framework ANSYS Fluent for all the different models. And we use a transient solver for most of them, using a small time step and a coupled pressure-based solver. In previous works, we did a mesh study and found that the best compromise between accuracy and computation time was around 30,000 cells. And for a discretization scheme, we use a second order upwind scheme. We judge whether the results are converged based on the lack of mass conservation or the mass flow rate error, and also steady residuals over a period of time. So I will quickly go through some of the results because some of them are less accurate than others. First of all, the HEM gave very stable and fast results, as has been discussed in previous works. we found that it would typically converge within less than 100,000 iterations, in some cases 20,000 iterations. And in general, it was quite accurate, as previously noted, for high motive pressure conditions. You can see on the right in the table that the best case was case 18, where the motive nozzle was less than 1% off. While for lower pressure cases, such as 1 and 9, the error is much larger. For the HRM, unfortunately, this implementation was unstable for many of the operating conditions. This is likely due to a programming or a instability problem. However, in general, for the points that did converge, we achieved similar accuracy and convergence rates at the HEM. The third model is the mixture model. This one, as has been shown in the literature from previous works, is typically very unstable and can quickly explode, let's say, and is also associated with very slow convergence. So for our case, we ran simulations up to 10 million iterations, which is more than 1 week of CPU time. And since these operating conditions are unknown, we saw that we had to cut the results before a converged solution was found. Unfortunately, the results were still oscillating, and we reached poor convergence. So these were not into the comparison. And the last model is the two-fluid model. From the previous results, we found that it has decent stability properties. In general, we had some numerical stiffness issues, especially in the motive nozzle for certain operating conditions. But it can reach quite reasonable results for the motive mass flow rate with given tuned parameters. However, we've concluded that more work is necessary on the submodels to at least get good accuracy for the suction mass flow rate. So in conclusion, we have found that of all the models, we can typically get reasonable accuracy, especially for the motive mass flow rate prediction, especially for the high pressure motive conditions. However, for suction mass flow rate, the accuracy is generally very poor, and you can have between 0 and 100% error compared to experiments. So a concluding remark is that further work is necessary to improve the accuracy and convergence rates. And especially for some of the more advanced models, we would prefer to have them converge in a lot reduced time. I would like to end with acknowledging HIF for funding the research, and I would like to say thank you, and I will take any questions.
Thank you for a very nice presentation. I'm always amazed about all the simulation that is going on. I see there's no questions for you here. Have you modeled or used the ejectors for transport of oil also, or looked at it, how it looks?
So this is actually a very interesting area, and there's this is really something we want to look at in the future, and preferably very soon, because it's a very interesting problem. Unfortunately,
it would be only a one-phase thing, you know.
Yeah. So in theory, that is quite a reasonable possibility, and especially for one-phase simulations, that would be definitely something to look at in the future.
Thank you very much. I don't know if there's anybody that has a question. Otherwise, thank you very much, and nice presentation.
Thank you.
And we will move on to the next speaker, which is Marcel Ulrich Ardens, who is a student at the NTNU in Trondheim also, and comes with a master's degree from TU Braunschweig in Germany. And he is also working with natural refrigerants. In this case, it's about heat pumps. The floor is yours.
Good afternoon. My name is Marcel Ulrich Ahrens, and I'm a PhD candidate at the Norwegian University of Science and Technology in Trondheim. Today, I want to use the next 12 minutes to present our work with the title Modeling Approach for Water Liquid Injected Ammonia Water Screw Compressor, which is part of my PhD project, which is focusing on high temperature heat pump solutions using natural refrigerants. Within this presentation, I want to explain our motivation and objectives, give you a description of the combined absorption compression heat pump system, introduce our modeling approach, and finalize the presentation with our conclusions and an outlook. Motivation and objectives. So the current situation is that the functionality of the combined absorption heat pump system has already been proven, and it was also used in first application in the industrial sector. Nevertheless, there are a lot of improvement potentials, as for instance the increase the achievable thing outlet temperature. For this, the compressors were identified as main constraint to achieve higher thing outlet temperatures, and the use of liquid injected screw compressors has been identified as a promising approach to overcome these problems and solve the challenges. The objectives of this work is the development of a modeling approach for the first identification of required modifications and suitable operating conditions of such a screw compressor, because we found that there is nothing available on the market. So we have to discuss modifications with the manufacturer and evaluate it ourselves. The second, the investigation on the effects of liquid injection. So it's a complex process. So we want to see how this affects the compressor and the whole heat pump system, or the performance of the heat pump system. And the last one is the planning and preparation of experimental results for later stage and subsequent evaluation and validation of the. First, I want to introduce the combined absorption compression heat pump system to you and give a description of the advantages of this system. On the left side, you see a schematic representation of this system, and it's simplified the vapor compression heat pump cycle with an additional liquid circuit. The idea for this goes back to the Olsenburg cycle, which was developed 1895, and we're using ammonia water mixture as refrigerant. Due to this mixture, we have different compositions at different points, which are shown here as rich solution, lean solution, and vapor. The system itself has the advantage that it's possible to achieve a high temperature lift from the low pressure to the high pressure side. And additionally, we have temperature glides at the absorber and desorber, which can be matched to the heat source and heat sink. Compared to other systems, we have lower pressure levels required to achieve these temperature lifts and also high temperature levels. And due to this mixture we use, we have additional degrees of freedom. So we can modify the composition of how much ammonia, how much water we put in the system or charge the system. And additionally, we can play around with the ratio of how much we pump or lead through the compressor. So this gives us some flexibility of the system. Today, the focus is on the compressor. And for the liquid injection, we are looking into the lean, or taking some of the lean solution after the solution pump and inject it in the compressor. Now I want to talk about the characteristics and requirements for compressors used in this heat pump system. We have different requirements stated here. So the material needs to be compatible so that we can use it with ammonia. The compressor needs to withstand high discharge temperatures, that it can be used in this high temperature heat pump applications. We need some kind of liquid resistance due to the fact that we always have water content in the ammonia. It's possible that it will condense. And on the other side, since we want to go to liquid injection, we will have definitely liquid content. And the last one is oil-free operation is desired so that we can remove the oil from the system. So all of these leads us to the use of liquid injected screw compressors. And here on the right side, you see a schematic representation of a twin screw compressor rotors. So the suction side is here, then the gas gets sucked in, compressed, and discharged to the outlet. The liquid injection itself has a positive influence and serves different functions in this process. So, for instance, the liquid will help to reduce the temperature during this compression process, but also serve for lubrication and sealing between the rotors, for instance. But nevertheless, on the other side, we also have a complexity of the process that leads to various challenges. So, for instance, we need to figure out where to place the injection port, or do we have more ports? How much do we inject at each of these ports and how? So, for instance, the size of droplets. And the last point is that the ammonia-water mixture as theotropic mixture in the two-phase process represents a special challenge, meaning the thermodynamic behavior. So all of this concludes that the use of thermodynamic and mathematical models will help us to gain a better understanding of the injection process. For the development of the modeling approach, we started with the identification of existing modeling approaches in the literature, and we found a large number of models varying in complexity and scope, and they can be divided into three groups. The first one is the empirical approach based on curve fitting or statistical data analysis, which is a bit difficult in our case due to the very little test data available for our specific application. The second one is the analytic approach based on pressure volume diagrams developed on analytic curves, for instance, polytropic curves or test data. Here, due to the theotropic ammonia-water mixture, the analytic approach might involve uncertainties and challenges, has to be included. However, employing analytic curves to a certain extent can be effective to simplify complex thermodynamic problems, so we will come back to this later. The third group is the numerical approach, which varies from one-dimensional up to three-dimensional or CFD models. So the quasi-one-dimensional models are based on mass and energy conservation equations, and the three-dimensional models divide the chamber into a large number of finite elements. And additionally to the mass and energy, we also apply the conservation of momentum. So for our case, we focus on the quasi-one-dimensional numerical models. Based on the knowledge we gained from the literature review, we developed our own screw compressor model using the Modelica language. In here, we have a quasi-one-dimensional model with multiple control volumes for each of the rotor cavities, and with the assumption of homogeneous conditions. As you can see here in the representation, so each of these look like piston is a control volume and represents one of the rotor cavities we have. And the volume changed with time. So going from the inlet to the outlet port, the volume will decrease due to this compression process. And we have liquid injection flexible in between, so we can place it wherever we want. Then mass flow will enter the cavity or the control volume. And this concept leads to different pressure, temperature, mass, and internal energy in each of these control volumes at each point in time. And of course, mass and leakage flows are determined. So we have leakage flows going backwards to the following cavity due to the pressure difference mainly, and the area we have in between, for instance, the rotor tips. And also we have the mass flows coming in at the suction and injection and going out as the discharge. So here we also modeled the areas to show when will the mass flow inlet outlet occur. So in total we can say that the model considers the effects of leakage flows, heat losses, and liquid injection, and it can be used for both steady state and transit analysis of such phenomena. In addition to the Modelica model, we developed a two-phase compression model using the engineering equation solver to compensate for any inaccuracies due to this ammonia-water mixture and two-phase compression. And here, the total volume is divided into variable segments with mass and energy flows going through the segments. So the position is fixed, contrary to the moving control volumes I explained before. Here we used polytropic relations to simplify the calculations between the suction and discharge port. The liquid injection is performed in a single segment, so in each of these segments can be selected and then the injection will occur. Ammonia evaporation at superheat is expected, and backflows, condensation, and/or absorption processes are considered in each of these segments, as you can see in the schematics for the mass flow and the energy flows. Additionally, a non-equilibrium factor for each segment was implemented to compensate this homogeneous approach from the Modelica model, and so we want to use these model for detailed thermodynamic analysis to support basically the Modelica. In conclusion, we can state that a model for investigating different compressor configuration without extensive database and/or experiments was required. Within this work, a modeling approach for liquid injected screw compressors was developed, and the model considered the effects of leakage flows, heat losses, and liquid injection, and can be used for both steady state and transient analysis. The comparatively low complexity allows the required flexibility to change, for instance, the number of control volumes, the size of the volume, the number of injection parts, the position, and also the amount of liquid that is injected. A two-phase model to compensate for any inequivalencies related to the two-phase compression process was developed and presented to support the developed Modelica model. And in the further course of the project, the model will be extensively tested, evaluated, and verified for the investigation of different arrangements and conditions. This work is part of HIIR, Center for an Energy Efficient and Competitive Industry for the Future, and we at the authors gratefully acknowledge the financial support from the Research Council of Norway and user partners of HIIR. Now I want to thank you for your attention, and I'm open to answer your questions.
Thank you very much for your nice presentation. I don't know if there's coming any questions on Slido at the moment. It seems not to be. I don't know if we wait a second. It seems not to be the case. Thank you very much for your very interesting presentation.
Thank you.
It is a type of system I have been looking quite a lot at. I find it very interesting. Thank you.
Thank you very much.
The next speaker will be Ekaterini Krisi, who has been working with Danfoss the latest 10 years as a technology expert in CO2 systems. She is cooperating closely with academia and research institutes like NTNU and SINTEF. Ekaterini, the floor is yours.
Thank you very much. I hope you all can hear me, and good afternoon to everybody. The work I will present today is about is an investigation of how can we calculate ejector performance of an ejector which is installed in a real system with data that we are getting from data acquisition system. The work is part of the multi-pack framework founded by European Union Horizon 2020, and a part of this project is a demonstration of integrated heating and cooling packages for buildings with high energy demand. In the study, we are utilizing a supermarket which is located in Portugal. The supermarket is, the system for the supermarket has two circuits, one for the refrigeration part and one for the air handling unit, which is heating and cooling of space. It's a booster system with CO2 parallel compression and 3 different kinds of ejectors supporting 3 different functions. two data acquisition systems are in this particular installation, and it's running since beginning of 2019. And we have 5 mass flow meters that are measuring the mass flow for the evaporator. So they're located in the inlet of the evaporators. The 3 different ejectors are serving, as I mentioned, 3 different functions. And we have the liquid ejector that is pumping liquid from the suction accumulator up to the receiver, enable the empty evaporators to run with a theoretical zero superheat, or overfeed, as people used to call it. Then we have the high pressure lift ejectors that they're pumping part of the gas from the suction accumulator up to the receiver. And both liquid and HP are supporting the refrigeration circuit of the system. And then we have the low pressure lift ejectors that they are serving the air handling part, the air conditioning. So the air conditioning is fed by liquid from the receiver, and the LP ejector is compressing the gas from the air handling unit back to the receiver. We have done measurements with different modes in different weeks where we have only one of these ejector families functioning. And this is the way, these are the data you are utilizing to analyze and understand the performance of each of the ejectors. When we're talking about performance, we have 2 main parameters: the pressure lift. So it's showing the amount of pressure that the ejector can pump or compress. And it's the difference between the outlet pressure of the compressor and the suction pressure. And this is based on measurement. And the entrainment ratio that shows how much the ejector can pump or compress. And it's this is a ratio between the mass flow of the suction nozzle of the ejector over the mass flow of the motive nozzle of the compressor. There is a challenge here to have mass flow meters in the inlets of the ejector. So we need to find a different way to calculate the performance. 2 methods are presented here. One is based on the performance of the component, and in particular case is the ROM model for the multi-ejector manufactured by Danfoss. And the other method is to utilize the mass flow balance in the system and the flow paths in the system, and utilize the data-driven model for the calculation of the compressors, mass flow of the compressors. The ROM model was developed in the Silesian University in collaboration with SINTEF and Danfoss. It's based on laboratory data and CFD simulations for the individual cartridges, and it utilizes orthogonal decomposition and radial base function. The model has some defined envelopes for the operation of the inlet of the mass flow and the section. And outside of those design envelopes, there is no verification of the accuracy and the validity of the model. Otherwise, it's quite easy to use, using as an input the motive nozzle and suction nozzle condition, pressure, temperature, and the pressure at the outlet. And as an output, we get the mass flow and the suction and motive flow. Hence, we can calculate the entrainment ratio. For the utilizing a data-driven model, the data-driven model was presented earlier today in an early morning session by my colleague Vahil Hosseini. We utilize the mass flow, compressor's mass flow from this model, trained model, to calculate the mass flow in the nozzles of the ejectors. The nozzles, the mass flow in the nozzle of the ejector now is written as a function of the compressor mass flow, evaporator mass flow, and high pressure valve mass flow. Following and keeping always the mass flow balance in the system. The high pressure valve mass flows are coming again from the performance function of the component. In that case, it's also downforce valve. The evaporators mass flow from measurements, and the compressors, as we mentioned, from this data-driven method. The data-driven method that gives some accuracy in the area of plus minus 10%. We ought to have in account that everything is in a certain level of inaccuracy or accuracy. We have a certain level of accuracy in the mass flow, the measurements, so we have a certain level of accuracy in also the functions. If we see now the results, if we take the LP ejector data only from the period that only the LP ejector, low pressure liquid ejector, was operating, with cyan color is the data from the data-driven model, while with red is from the ROM model. We can see that both models are following the same trend. But the data-driven model is overestimating. That can be due to an overestimation from the function of the polynomial function from the high pressure valves. We cannot say which one is more accurate than the other, but the levels looks reasonable and they follow the same trend. If we go to the liquid ejector, we have to take in account that the liquid ejector is on or off, sometimes but sometimes doesn't. So in the bottom figure, we can see the ejector status is average every 10 minutes. The data-driven model, which is the cyan color again, it's following those trends, it's following very well the on-off operation of the ejector. In the ROM model, we have coded this on-off operation, but we can see that it's a huge overestimation in the ROM model. This might be because some of the CFD data, in some cases, they overestimate the section mass flow due to not being able to capture the non-equilibrium status in the ejector. And it looks a little bit not reasonable in some of those points. So we reconstruct the performance function by utilizing only the lab map data, and we can see a better accuracy or comparison between the two models, same trends and similar levels. For the high pressure lift ejectors, the verification parameter here is the ambient temperature. We have some variation of day and night, and that is also reflected to the load of the system. We can see that the data-driven model is also following the trends of the day-nights, different loads. And the levels we are getting, they are not unrealistic compared with what we know from lab data of the individual cartridges. The red line of the ROM model is not following the same trend of the ambient temperature, doesn't follow the same trend with the data-driven. But there is a reason for that. The reason is that we are utilizing outside of the operational envelope. Superheating the ROM model is a maximum of 15 Kelvin, superheating the suction nozzle. Here in the data we have, when we have only HP ejectors, then the superheat was over 22 Kelvins. So it's outside of the operational levels. It doesn't work. We cannot verify that it's working. If I conclude, the work was to find a way, how can we calculate the performance of the ejectors when we don't have the mass flow meter, so we lack measurements. It seems that the utilization of a well-trained data-driven model can support us. So we can calculate compressor mass flow from the data-driven model, and they utilize that in the calculation of the performance of the ejector. Reduce order model for a multi-ejector, it's giving realistic results only when it's used inside the design operational envelope. On the multi-part project, we have some further developments. We are focusing on developing a further modelica model for this particular supermarket. So some work will be continue and try to analyze and verify mass flow and ejector performances. Thank you very much for your attention.
Thank you very much for a very nice presentation. And I hope there is a number of questions. However, I have to say it looks as if the audience are not really able to come with questions.
Alex, maybe
Can
I have one question.
Yeah.
I would like to know if there are any basic values when to decide for vapor ejector, wet ejector, overfed evaporator, parallel compression. If there are some temperatures, pressure differences or something like that, we can make an easy decision, for example, for the region Warsaw. If you will be in Warsaw, what will be the basic value you will use for that for such decisions?
There are the main parameter that will define which is the best system to use is the ambient temperature, the climate where we want to apply it. And always in a seasonal performance ratio, CPR, can be calculated that give us a better understanding which of all these technologies can be utilized and where. There have been studies actually presenting Gustav Lorentzen in 2018 a paper where we had different technologies of the ejector. We had booster system, parallel system, ejector liquid, and ejector with low pressure like a booster system, and high pressure. And we applied a modeling work with calculating CPR in different locations and showing where each of those technologies can give a better benefit, and also in which of those locations it has a commercial meaning. That means that the investment return is in a reasonable time. So there have been studies, and there are more and more studies focusing on where and how can we choose which of those technologies is better for which location. But if we just make it simple, a calculation of seasonal efficient performance ratio is the easiest. It includes COP, and it includes the climate from the climate temperature of the area.
So the climate is very important. Yes. So is the technology with these all possibilities suitable for all the climates in the world, or there are...
If I make it simple here, if we're talking about high pressure ejectors, there is no need to do this investment up in Denmark or in Norway. We won't have any benefits. But if we go south of Paris, so we go to Madrid, Spain, Greece, then there is a significant improvement. It's an improvement on the level 5–10%, which if we translate it on the bill we are paying for the electricity, is a significant amount. If we talk about liquid ejectors, like running overfed evaporators, pumping the liquid, that is independent of the climate. We can have this solution up in Norway or south in Greece, and it will provide the same benefits, because what it does, it increases the suction pressure of the empty evaporator. And if we have a reasonable multi-level load, then it always provides similar benefits. And then the other thing we have to take in account is the system itself. So we cannot, when we start talking about increasing one pressure in empty, decreasing the delta P of the compressor, we have to understand that that cannot be applied in any system, because if all of a sudden we have an LT load, which is huge, is the same level with the empty load, then if we increase the empty pressure by utilizing LT liquid ejector, we won't get benefits because we'll increase the LT compressor. So two things. One is the climate. We have to take into account ambient condition, operation of our system. Second thing, design of the system.
Okay, thank you.
I hope I answered.
Fine, thank you.
Thank you very much for the questions and answers. And we will go to the next speaker, the last one for today. It is Josef Sedlak, engineering and study at Electrotechnical Faculty, Technical University of Košice, I don't know. Senior product engineer with 18 years experience in compressors at Embraco, Slovakia. The floor is yours, Josef.
Good afternoon, ladies and gentlemen. My name is Josef Sedliak, and I work for Embraco Nidal Global Appliance, located in Slovakia, and I would like to present the possibility to use propylene as a refrigerant for commercial applications. Before going to speak about propylene, let's make a summary on the key drivers which are affecting the applications of refrigerants in Europe. So basically we have three main drivers. The first one is very well known, F-gas regulation 517 from 2014, which from January 1st last year it's allowed to use only refrigerants with GWP less than 2500. This is valid for all applications except ultra low temperature systems, which are used to store the products below minus 50 degrees C. From January 1st, 2022, for commercial freezers and refrigerators, it will be allowed to use only gases with GWP less than 150. What does it mean? It means that from 2022, for the most of the light commercial systems, flammable gases will be used, or hydrocarbons, or low GWP A12s, if you don't consider CO2 for very large systems. Linked to the F-gas regulation, the second driver is the charge limit from flammable refrigerants. Most of the equipment in the light commercial segment are approved according to product standard 6035-2-89, which recently in 2019 the ISC version was updated in terms of the charge limit for flammable refrigerants. So the new edition 3 of this ISC standard is allowing charge for flammable refrigerants up to 13 times LFL for a single circuit, but not more than 1.2 kg. For instant propane, it's allowed to apply the charge up to 500 grams, but for A2Ls, refrigerant R455A, theoretically it can be used 5.6 kg, but the standard is limiting to maximum 1.2 kg. Basically now we are waiting for releasing of European version of this edition 3, and according to the last information it should be released in last quarter of this year. The third driver is related to the energy regulations, which are coming in force soon in March 2021. There are 2 regulations, and they are related to equipment with direct sales function, like a supermarket, refrigerating cabinets, beverage coolers, ice cream freezers, and vending machines. First energy regulation is related to the new energy requirements, and also called Lot 12. And second regulation is related to the obligation for energy labeling of these systems. So each system must have an energy label. Now let's have a look on the near future map of refrigerants for different type of commercial applications. The mainstream of light commercial systems like chest freezers, bottle coolers, vending machines, professional kitchen equipment, refrigerated display cabinets. So they all will use hydrocarbons, so isobutane or propane, with option the on-off or variable speed compressors. Special equipment like ultra-low freezers, which are built for medical or laboratory purpose and currently used for storage of COVID vaccines at -80°C, they already use hydrocarbons, propane on first stage and ethane on the second stage. Regarding the other systems like cold rooms and remote systems, which require higher charges, and they use for their approval general safety standards EN 378. Propane can be used for the smaller cold rooms, but for the larger cold rooms, we expect low GWP actual refrigerants will be used. And CO2 makes sense for larger capacity supermarket systems above 5 kW. Let's talk now about other natural gas propylene, which can be also other low GWP alternative to HFCs like propane. Propylene belongs to hydrocarbons. It's also highly flammable gas belonging to A3 classification. It's not toxic. It has one double bond. And unlike the propylene has natural pungent smell, so the potential leakage can be easier detected. Comparing to propane, it has higher LFL value, which according to the new limit 13 times LFL in IEC 63335-2-89 edition 3 results in 100 grams more of allowed charge limit. Basic thermodynamic analysis performed at EN 12,900 MBP conditions is showing higher specific cooling capacity, which is good because comparing to propane, we can keep similar displacements to 404A compressor and achieve high efficiency like propane. So propylene is providing higher capacities and higher charge limit comparing to propane. Looking on the pressures, propylene has higher pressure than propane but lower than 404A. It's somewhere in the middle. So if you want to use the propane compressor for propylene, we must optimize the motor for higher loads. So in terms of the motor sizing, it's close to 404A design. These higher pressures have for sure negative impact for the compliance with pressure directive, and analyzing the pressures at 43 degrees C, the pressure is 1.2 times higher than propane. So if the compressor with propane belongs to category 1, it needs to be double checked because with propylene it can fall to category 2. How to understand better the performance of propylene? We did comparative calorimeter tests on NJX low back pressure compressor, and we compare the performance with other gases like 452A, which is transitory gas, and propane to original 404A. From the relative capacity chart, we can see clearly the benefit in cooling capacity comparing to propane. At higher evaporating temperatures, the capacity is equal or even a little bit higher than 404A. In terms of capacity, it should be also mentioned here that propylene has high heat transfer coefficient, which was studied and published by University of Padova. Looking on the relative efficiency chart compared to 404A, we can see the similar behavior as propane. So at higher evaporating temperature, we can see huge benefit in efficiency comparing to 404A. It's almost 20%. So the curves, efficiency curves, are very similar, propane and propylene. Talking about reliability of propylene, we have analyzed solubility chart and Daniel plot of kinematic viscosity of propylene with polyester oil, and it has shown acceptable results. For example, compared to 448, and the reliability was confirmed by live testing at high load conditions and high compression ratio with very positive results. So in the end of the presentation, some conclusions. So propylene can be a low GWP alternative to HFCs, similar to propane, providing higher specific cooling capacity, which can be a solution in some specific cases. Propylene has very good thermodynamic efficiency, similar to propane, so we can obtain very similar efficiencies like propane. Propylene has higher pressures, so motor needs to be optimized, and compliance with pressure directive in Europe needs to be evaluated. Reliability tests show good results with the same oil as is used for propane or 404A. So that's all from my side. Thank you for your attention, and it will be a pleasure to answer your questions. Thank you.
Thank you, sir, for a very nice presentation. So I can see if I can get on here with my screen. Is there any questions? Please use Slido. Here comes it. Yes. What are the motor and discharge temperatures of 1270 versus 290?
Actually, the temperatures are a little bit higher. Discharge temperatures are a little bit higher of propylene comparing to propane. And in terms of the motor temperature, this test is planned. So I don't have the exact values in the hand. So we need to wait some time for these results. But the discharge temperature is higher than propane. So for sure, propane has some advantage.
What is the what do you call it, the recommended superheat for these refrigerants?
I think very similar as propane. So because propane is it's a very cold refrigerant in terms of the internal thermomap of the compressor. So the delta which between the propylene and propane is not so dramatic that should lead to the reduction of superheat.
Because in my experience, I only worked with propylene and 290 for 25 years. There we need some superheat. That is why I ask. Otherwise, you will not get boiled out the refrigerant of the oil.
Mm-hmm.
Any other questions?
Joseph, if propylene is better in most parameters as you have presented, what is the main reason that propylene is not so widely used as propane?
Good question. In some countries, like US, the EPA basically didn't allow to use propylene because of the human comfort, because there is some, as I said, some smell inside the propylene, but it's let's say natural. So they are a little bit restricted to use the propylene in the, for example, in the air conditioning. Okay. Basically, the thermodynamic properties are very similar, and we made many developments for propane, but I think propane is widely used refrigerant. Okay, and maybe this pungent smell can be some restriction for use in some applications. Okay.
Actually, it's a mandatory thing in some countries, for example, Australia, to have this smell put into the gas. So if you want to do it with propane, you have to put in mercaptan, whereas the 1270 has the smell naturally, as you also mentioned. And that's why a lot of people, they actually like propylene or propene, as it is correctly now. So I agree with Peter when asking why is it that we are not using more propylene. But I think one of the reasons is that, for example, BITSA is actually recommending only using propane for temperatures below -10 degrees, and based on their experiences. So I guess that is one of the reasons.
Yeah, we don't have so much experience basically with propylene, so we did some study, and based on the first results, it looks a very interesting gas, okay, for commercial applications.
The next question is, could R1270 be used with 290 Embraco compressors?
Actually, as I mentioned in the presentation, the propylene has higher pressures than propane, so the motor needs to be optimized for these higher loads. Okay, so actually not. Okay, it must be checked because the overload can trip, and the motor temperature might be higher than specification in the standard, in IC standard.
Okay, if there's no more questions.
May I ask if there any problem with this chemical that there is two bounds in this propylene, and in propane it is only one bound? Also, is there any problem with this chemical?
It was, if I may, it was a very discussed topic in the beginning of in the end of 1995, 96. We discussed it widely, and the end was that in a clean and nice system, you will have no problems with 1270 because the double bound is the topic that you are looking at, but it doesn't seem to under normal circumstances in a refrigeration system be a problem. Whereas if you go very high, over 110 degrees or something like that, you can get the problem, but you don't see it in normal refrigeration.
Yeah, we also did the compatibility testing according to the ISE standard, and it passed the testing. So no problem.
Okay, thank you.
There is a question, do you plan to develop 1270 compressors?
Yeah, actually, as I said, we are in the beginning of the feasibility study. So let's see what will be the future. If there will be some demand from the market, for sure. It looks very interesting.
So when do you expect to be able to say yes or no?
Good question. Maybe end of this year.
Okay, very good. Then we have something.
Mm-hmm.
We will come back to you. Thank you very much for your nice presentation. May I remind you that there is a closing ceremony here at 1700 hours. I don't know if you have something to add to this, Peter.
No, everybody will be welcome on the closing because there is a nice program. So please join us.
Join us.